Hello, in this video I'm going to give you a broad picture of the reactions involved in this chapter. So the reactions we are going to explore involve the transformation of an alkene into other functional groups. For example, we can transform an alkene into alkyl halide, where the halogen is installed in a more substituted position, or we can direct that halogen to a less substituted position. We can be able to transform an alkene into an alcohol with the hydroxyl group being in a more substituted position, or we can direct it to a less substituted position. We can also be able to transform an alkene into an alkane by doing a reduction to install hydrogen across the double bonds. We can do halogenation to form a dihalide, that is an alkyl dihalide. We can also be able to use a halogen and a weak nucleophile like water in this case, and that will form a halohydrine, where we have a halogen with the hydroxyl group. We can be able to transform an alkene into a diol by directing the hydroxyl groups onto the opposite sides. That is what we call anti-dihydroxylation. Or we can direct the hydroxyl groups to the same side, what we call syn dihydroxylation. Another reaction we could do is to cleave this double bond. When we cleave it, we can end up forming a compound that has a ketone functional group and an aldehyde. What we're going to look at is the common trends that you will experience in these reactions. I'm going to use hydrohalogenation as an example. So in hydrohalogenation, we are adding a halogen across the double bond onto one of the carbons, and then the other one is going to be a hydrogen. If these carbons differ such that one of them is more substituted and the other one is less substituted, then it implies that after doing a proton transfer followed by loss of leaving group, we are going to have a regioselective reaction where the intermediate formed could lead to a more stable carbocation ion or a less stable carbocation ion. We know that a more stable carbocation ion is going to be favored, and the reaction here is going to involve SN1, where the leaving group that was kicked out is going to come back as a nucleophile to do an SN1 reaction. So we end up with a nucleophile in the tertiary position, or we can have the nucleophile in the secondary position. When we have the nucleophile installed in the more stable position, the more substituted position, we call that Markovnikov addition. When you have that incoming group installed in the less substituted position, we call it anti-Markovnikov addition. If we want to install that nucleophile in the less substituted position, then we need to use a peroxide, where this R could be an alkyl group or it could be a hydrogen. For example, if we use hydrogen peroxide, we can direct the synthesis to give us specifically the anti-Markovnikov product as the major one. The mechanism of this reaction involves a free radical step that we will learn later in chapter 10. Assuming we have a situation where the intermediate formed is going to be less stable, but there's a possibility to rearrange, then a rearrangement will occur. So like in this case, we are going to have a proton transfer followed by loss of leaving group. And then we form the secondary carbocation ion, which will then undergo a 1,2 hydride shift to transform into a tertiary carbocation ion. Then the nucleophile is going to undergo the SN1 attack, and then we end up forming the product. So when that happens, still the major product is the one that forms the stable intermediate. So we end up forming Markovnikov addition product. Okay. The other fact I want us to consider is we know that this is an SN1 reaction. In an SN1 reaction, we form the intermediate. That intermediate is going to be planar. So the bond angle here is going to be 120 degrees, 120 degrees for that, another 120 degrees over there. So because it is planar, the incoming nucleophile can either attack from the bottom in this case, or it can attack from the top. So what we would call either front side attack or a back side attack. And when that happens, we're going to end up with enantiomers. That is, one of them is going to have the opposite configuration of the other one. To explore other stereochemical aspects, I want us to consider halogenation. So in a halogenation reaction, we end up with what we call the anti-addition. So one bromine atom is installed on the opposite side of the other one. Now what happens in this case is we're going to use the pi bond as the nucleophile to do a nucleophilic attack followed by loss of leaving group. So we are supposed to have a plus charge over here, but that plus charge is stabilized by the electrons from the bromine. And when it stabilizes that, it means that the bromonium ion is above the ring, then the incoming group must attack from the bottom. So we end up with what is called anti-addition, which leads to the formation of trans product. That is, one of the bromine is at the bottom, another one is at the top, and they're similar compounds, so we use the trans notation. This can also be experienced in the halohydrin formation. In this case, again, we are going to have the pi bond acting as the nucleophile, so it does nucleophilic attack followed by loss of leaving group, and then the positive charge that's supposed to be here is going to be stabilized by the bromonium ion. So once the bromonium ion is formed, we can use a nucleophile, even weak nucleophiles, to attack the electrophilic position. So this again is an SN1 mechanism, and then we end up with the product where the hydroxyl group is installed in a position which is anti, that is on the opposite side of the bromine. They are on the same plane but on the opposite sides. Sometimes even an alcohol could be used as one of the weak nucleophiles to install the ethoxy group over there. Now let us look at the stereochemical outcome in terms of dihydroxylation. In the dihydroxylation, what we do is to transform the alkene into a diol. So for example, how can we transform the alkene into a transdiol? Now what happens in this case is we can use a peroxy acid such as MCPBA. MCPBA is the structure you see over here. So it is just like a carboxylic acid, but it has an extra oxygen. So it can be able to have that oxygen installed across the double bond here, and that forms an epoxide. An epoxide is a three-membered ring where one of the atoms is an oxygen. So this reaction usually generates a trans-diol. It involves two steps. The first step is the epoxidation, and then the second step is the installation of the diol. The epoxidation process involves a concerted mechanism which dictates that the atoms involved must be on the same phase with each other. After the epoxide is formed, the next step is to react it with water. But water is not a good nucleophile. So if we use water to attack this position, the reverse reaction is likely to be favored. So to make sure that the forward reaction is favored, we can add an acid. Then now the water can attack the electrophile and we form a hydroxyl group, and then we end up installing the next one after doing the proton transfer to generate the diol in anti-addition format. If the intention is to form the diols on the same side, then we can do a concerted mechanism using osmium tetroxide. Once we do a concerted mechanism, there is no more nucleophilic attack, so what happens is we can add water. The water is simply going to cleave off the osmium and transform it into a salt, and then the alkoxide picks a proton and we end up with the product.